Welcome to Gauntlet HQ here in Austin, Texas. We're here in the atrium. This is the exact location where we have real classes for Gauntlet AI, and we wanted to make night school so you can see what it feels like to be a challenger. The topic I'm going to be covering today is software factories. And the reason why we're covering software factories is because they're becoming more and more commonplace across multiple companies. Today, we're going to be talking about minimum viable factory, what it takes to build a factory that generates an app end-to-end for you. The way this is going to work is we'll do about 30 to 45 minutes of the lecture. Halfway through the lecture, I'll stop for Q&A, and then at the end, I'll also stop for Q&A. I've also prepared a repository for you guys, so you can actually take what you learn in the lecture and then go apply it yourselves, hands-on keyboard, and actually try this thing out. Are we good to go? All right, so we're gonna start with some slides here. What if you stopped writing software and started managing the things that write it for you? We predict in the future, within the next decade, a software engineer is no longer the actor in a movie. They're the director of multiple agents that are writing software. That means a software engineer gets to manage these AI coworkers. These AI software engineers are gonna go about, build software, come back together, and then compile the entire thing. We're preparing for a future where this is the case. A software factory is exactly that. Let's say that we no longer had to do the day-to-day rigmarole of trying to type in code or trying to check every single aspect of what we're building. What if we could build a harness? What if we could build an entire factory that would take everything step by step, build it based on our criteria, and as a result, launch that for us directly? First, what we used to do is, hey, here's that manual line of code. Here's that one single Claude code session. What we want to go now and do now is take multiple sessions over time and see if we can conduct them, see if we can orchestrate them, see if we have a layer on top that lets us actually see what is happening with the code. Why does this matter? The reason this matters is because the bottleneck is changing. The bottleneck before was, hey, developers have limited amount of time. And because they have a limited amount of time, we need, hey, a Kanban board, tickets, a product manager. We need to come together as a team and prioritize what we're building. But as a result, now with Claude Code, Codex, and all these coding agents, it is no longer bottleneck by the time to generate code. It's rather the bottleneck of making sure things are deployed correctly, that there's testing in place, that there's verification, and that we have clear specs for the coding agents to actually go out and build something. The patterns are already showing up. There's multiple apps in the market right now that let you conduct multiple Claude Code instances, multiple Codex instances. We're seeing end-to-end pipelines, even the Replit agent running for more than 3 hours. These are deep agents that are doing work without human interaction. And because they're doing work without human interaction, the thing that we need to focus in on is what work are we actually giving them? How are they prioritizing work? And how are we verifying the actual output on the other side? Now, what I'm going to show you today is an experiment. This is not the perfect software factory. In fact, nobody has actually created the perfect software factory yet, right? You still need engineers to go in and take that final product from 80% all the way to 100%. So what we're going to show now is if we took every single step of that software factory, that includes creating a spec, that includes creating tickets, that includes creating subtasks, that includes adding tests, that includes deploying it to your deployment pipeline. All of these steps, if they were managed by agents, how would you build it? This is a thought exercise that I gave the Gauntlet students last week. It was a case study that they were asked to build their own software factory, a factory where they can give an idea and then the app would be outputted on the other side. Now, there's 4 questions that we want to answer as a result of this exercise. Can you actually take a ticket and turn it into a deployed web app? Is that web app actually even good? Like, is this actual usable code that multiple engineers can work on and would be considered production grade, whatever that term means? Does each agent fall apart under pressure? Is there a lot of context to manage? Do they tend to forget things that they're working on? Or can they go end to end for the creation of the software? And what is the smallest thing that this build can do for us? Does that mean that we can build a web app? Does that mean we can build multiple web apps? How much can we add in terms of load to the system? And that was the goal of building minimal viable factory. You're going to take away 4 things from this lesson. The 11 building blocks that I think every software factory needs. We're going to showcase how each of these agents coordinate and wire together. We're going to show how they talk to each other and where the record is stored. And then we're going to show the actual code for how this factory works. The thought process here is you can take my minimal viable factory and go build your own. Go to your company, take your tech stack, and start to build out the actual factory for you and your engineers. Now, what is a software factory? Imagine if you had a ticket and the ticket was deployed to an agent. Now, I want us to go 20, 30 years in the future where we have multiple coding agents that are available to us. We have a contract between us, the engineer, and the coding agent, which we call a spec. That spec is then handed off, and then the coding agent is able to do something on top of a code base or actually generate code from scratch. If this is the future, a software factory is you put in a contract, that contract outlines what you're actually going to be doing on top of the software, and as a result, it builds that out for you end to end without human interaction. Our thought process for this software factory, the minimal viable factory, was that we'd have one orchestrator on top. That orchestrator would be managing which agent was running. It would also deploy agents in parallel, and as a result, have its own Claude Code instance for each parallel agent. Afterward, we'd have review, we'd have testing, and then we'd deploy the entire thing to Vercel. Now, if you were to look at the smallest set of pieces that would make this work, this is what I really want you guys to focus in on. Because in the world of AI, tools matter less. Tools can change, but the framework or the toolkit that you use that pins all these tools together is what results in an outcome. So this is the framework. If there's nothing you take away from this class, but you take away this, then it will be worth it. First thing is you need a record. What are all of these agents going to make sure that they're working on the right thing? If there's multiple tasks being done in parallel, how is each agent deciding that, hey, I'm working on this file or I'm working on this other file? That record is the source of truth to ensure that there's multiple people working on this directly. We need some sort of memory because the memory is going to stay intact for every agent doing a task. Whether that's an MD file, whether that's a memory graph, whether that's memory being stored in the cloud on a database somewhere, we need memory which associates, hey, I've done this task, I've done this task, this is the next task I'm going to work on, this is what I've learned so far. You need the orchestrator because the orchestrator is actually what's putting up multiple instances of Claude Code. It's the thing that is actually moving the factory forward. Similar to a manager on top of an assembly line, if you don't have an orchestrator, then all you're really doing is people working disconnected without a true goal or mission. You need some sort of execution environment. So in the case of what we're building today, we're going to be using Docker containers. But they could be sandboxes, they could be their own APIs, they could be different things that we use so that the agent can perform actions on top of the code base. If the agent is unable to perform actions in a safe environment with the right keys, then there's no point in actually building the factory. An agent runtime is the actual generator of code. So in this case, we're going to take Claude Max plans, we'll take different instances of Codex, and that's actually going to be what's generating code on top. The integration layer is essentially, hey, these are all the things that we're going to connect to for our software factory. That might be our Kanban board. That might be our deployment pipeline. That might be our testing strategy. That might be our database. Whatever it is, we need to integrate across all of those tools to make sure that we can talk to those tools directly. Now, quality gates. This means that I've built this factory similar to the way if toothpaste was going down an assembly line, there'd be one person to check the actual carton of toothpaste. We need quality gates for our software. Meaning, as soon as the spec is created, we'll have a gate to ensure that a human is checking that spec. As soon as the testing strategy is created, we'll have a gate to make sure that there's a human checking that test created, the test suite created itself. The goal here is add the human gates wherever you think your software is vulnerable. Meaning if you need it for testing, add it there. Meaning if you need it for something else, add it there. A delivery target is essentially the location where we're going to deploy everything. This could be Vercel, AWS, GCP, whatever you want. It could be whatever your company is currently working with. And that delivery target is essentially going to be the thing that we connect to and deploy to directly. Observability. Now, there's a lot of solutions in the market right now, but none of them have observability or visibility on what the software factory is actually doing. Because the software factory is doing so many things in containers, in the cloud, on your computer, as a result, there's less visibility into what's going on. So observability on top of the orchestrator, observability on everything that each of the code generators are doing through something like Langsmith. Finally, I'm going to have skills. Each of the skills represent a portion of domain knowledge that might be specific to the factory that I'm creating. In this case, I've made this factory for the tech stack that we usually use here at Gauntlet. That means I have a skill for code review. I have a skill for deployment. I have a skill for generating code. I have a skill for our testing strategy. But this is the domain knowledge of your engineering team so that you can capture that domain knowledge within your factory itself. Finally, identity and secrets. We're going to have to connect to a lot of things, hit a lot of APIs, access information wherever we need to. So we need some way to manage those secrets. Now, the awesome part about these primitives, you can swap them out for anything. If your company decides to use GCP, swap it out. If you decide that, hey, Codex is better than Claude Code, swap it out. But if you have this framework, if you have these 11 things in place, connecting them is what results in the software factory. Okay, so for this example, for class today, I'm going to be using Linear, our Kanban board, as our record of truth. Our memory is going to be MD files within the actual project directory. And we're going to have LangGraph as our orchestrator, so a graph-based agent that's actually executing things on top. Our execution environment is going to be Docker containers hosted locally. We're going to have Claude code within each of those containers that is actually deploying all of these agents. We're going to have 5 MCP connections: Linear, GitHub, Vercel, Supabase, and Slack. We're going to have interrupts, which are essentially a message sent to Slack for me to go out and review a spec, code that is being generated, or a testing strategy. And we're going to have our delivery target, which is going to be Vercel for our front end and our database on top of Supabase. Lastly, I've connected everything on top of the orchestrator and each of the agents to Langsmith for traces. That means I can actually see each of the devs working in parallel. I can see the spec being generated, and I can see the context in versus the output coming out. Lastly, I'm using skills on top of a .claude directory, which means that there's 6 markdown files which represent the domain knowledge of what we're building. Finally, for this minimum viable factory, all of my ENVs are just stored locally, so I can run the entire factory on my computer. Okay, before I continue, I'm going to take a step back and we're going to do some Q&A. So let's see any questions that are coming. The first question, which I think everybody tends to ask even in a Gauntlet class, is, will this be recorded? And if so, where can I find it? This is 100% being recorded, and it will be emailed to you directly afterward. What questions do we have on top of the software factory? Nothing yet? That's okay. That's totally fine. I might ask our live audience here, which is the cohort, if anything.
Someone said, is Meek Mill going to join?
Someone just asked if Meek Mill is going to join. The answer is no, not yet. But you never know. If we're doing night school, Meek Mill might show up at any time. So it's up to you to pay attention. I'll keep going, if anything. Okay. All right, we're going to talk about the pipeline. So this pipeline is going to walk you through how we built the minimum viable factory. Again, I want you to grasp the thought process behind what I'm trying to do. The thought process on how I set up the entire pipeline, how different aspects of the factory work together, and what each agent is doing for different areas. It all starts with a ticket inside of Linear. So what I did is I created a project, and that project was called Software Factory. Inside of that project, each issue is a different app that my software factory is currently building. Inside of that issue, the software factory can put updates, it can create subtasks, it can, as a result, use that ticket as a form of record or truth with a human being. So inside of this linear ticket, I'm putting a simple one-liner on what I want to build. Let's say it's a Trello clone. I'm also adding any necessary information on top that corresponds with the clone I'm trying to build or the application itself. This could be information on the UX UI. This could be information on the front end. This could be information on the back end. This could be information on how data travels across the board. This ticket is going to be essentially, in spec engineering, our request command. So if you've heard of spec engineering, the request command takes all of the knowledge across the board for UX, UI, product engineering, and that knowledge is then put into the ticket to create specs. Once I've created this ticket, it fires off a webhook to my factory. The factory gets all of the information when I put that ticket from backlog to in spec. Then the agent runs. And when the agent runs, it initializes a pipeline. The pipeline creates its own GitHub repository. That GitHub repository becomes the area in which we will create this application. We add our skills, our memory, our audit layer, so we can actually see what's going on directly. And we make sure that everything is actually set up to add code on top. This initialization is just to make sure that we have the stomping grounds for creating code. We have the area to add code. We're generating PRs on top. And as a result, that is what's going to be used for the code itself. The repo gets created. The Vercel project gets created. We have a Postgres database that's created. We add a memory file. We have subtask on linear. And all of a sudden, we start creating our actual spec. So this goes to a PM agent, and there's a specific skill associated with the PM agent on what to do and what to write. It uses this skill to basically say, hey, every spec should be formatted this way. This is the information it should include. This is how that information just transfer from one section to the next. And that agent is then going to write that spec and then write it to the ticket on top of linear. Once the spec is written, there's a gate that hits right away. And that gate is for human approval. So what I'm going to do is I'm going to get a message on Slack, which basically says, hey, go review the spec that was just generated. The spec is going to lay out exactly what is being built. I'm going to confirm that everything is correct. And then I'm going to move that to in architecture. The architecture step is going to take the spec, the information I've initially given it, and actually map out the entire system design. That could be client-server interactions. That could be how the database is set up. That could be how each of the architect designs the pieces or the components for the software that we're making. It also makes the tech stack decisions, just in case we need any extra libraries that are outside the regular libraries that we're already using. It creates the component tree, meaning the entire file structure of what's happening. And this file structure actually tells you, hey, these are the files that are going to be built and what code needs to go inside each one of them. After that, there's the numbered subtask, meaning we're going to create a spec, the architecture, the dev task in parallel. We're adding everything to the linear ticket because that's our record of truth. That's where everything's being stored. Once we create that, there's another gate. And the reason I put a gate here is because pre-search and system design is probably one of the most important steps when it comes to creating a software factory. You want to make sure that it follows the same terminology, the same methods, the same framework that you would normally follow for creating a web-based application. So in this scenario, what we're going to do is I'm going to walk through the architecture. I'm going to see the system design diagram. I'm going to confirm all the decisions that are being made. And once I've confirmed all the decisions, I'm going to then transfer the ticket in dev. Once we've transferred the ticket in dev, we're actually decomposing all of the tasks. All of the tasks then become, hey, these are all the tasks that can run in parallel for our software factory, and these are all of the tickets associated on top of linear. Each subtask can essentially be done without being interfered by another agent or a human being. So what we're going to do is we're going to spawn different Docker containers. Each Docker container is going to have a Claude code instance inside, and we're actually going to give it the information it needs through memory to actually start coding on top. It'll actually write the prompt as well for each of those Claude code instances. Now, each dev will focus on different subtasks, and all of those subtasks will come together in a single PR. What I'm having the system do is create a draft PR, and as it's adding code and committing code to that branch, you can actually see inside of the draft PR all the changes being made. All of these agents are running in parallel, and there could be an unlimited number of agents that are being created. Now, the orchestrator decides, hey, I'm going to create 3, I'm going to create 4, I'm going to create 2. And if you don't need to actually create an agent for each subtask, then it decides to just do it with a single agent. Now, we are going to then swarm on top for all of these dev agents to actually come in and actually code what we're trying to make. Once we've coded it, there's 2 verification steps that we've added. This is before human verification. The verification steps are a review agent and a testing agent. Now, we've generated a test suite already using one of our dev agents. So in this scenario, what we're doing is we're actually running that test suite. We're making sure that that test suite passes. And then as a result, we're then resolving different things on top. Each of these 2 agents are before a human being, but have a skill associated with them. So the review agent actually knows exactly what I'm usually looking for when I'm reviewing code. The testing agent is actually going to walk through the entire setup and as a result, see if everything is passing. Once everything is done, and I know that those edits have been made, then it goes to a different gate. And that gate is final human approval after testing and review. In this scenario, I can totally block this ticket. I can have it redo something. I can go check the deployed URL and make sure that it's actually building the thing that I want it to build. But you review it, you test it using skills that are already corresponding to the domain expertise of your team. And then you have the human gate. And the human gate is what results in whether or not the code passes. Now, let's say the code does pass. What happens next? What we're doing is we're merging that PR into main, so the main branch becomes our primary branch in which we have our code that is working. We push that front end to Vercel. We have a database connection to Superbase, which already are tie in well together. I've also added the Railway MCP. I've added the Superbase MCP. I've added the Vercel MCP. So I have a backup just in case something goes wrong or doesn't work. I then wait for that deployed URL, and I make sure that the deploy agent is able to use different commands to actually take that application all the way through. Okay, so this is the pipeline through the architecture. We'll start with the linear webhook, which is going to have the overview of the application that we're building. We're going to initialize the entire project. That means creating a repository. That means creating a Vercel project. That means creating a database associated with it. We're going to decide on what that schema is and start working on the architecture. The architecture is going to define the actual system, the client, the server, how those systems are interacting. And it's then going to go to a PM agent to make sure that we highlight all the functionality required for this job. We're going to have 2 gates, one checking the functionality and the spec that is generated, another checking the architecture and the plan that is generated. And those 2 gates are making sure that research planning is done properly before we start swarming with different agents. Now, once we start swarming, what we're doing is having the orchestrator decompose all of our tasks, make sure all of the tasks are divided into small subtasks. Then we're creating new dev agents based on the complexity of what we're building. These dev agents are essentially trying to build different things in parallel that don't hit each other. Then they're coming back and adding code to a draft PR. That draft PR is slowly being built up until it's ready to be reviewed. And then once it's ready to be reviewed, it's going from draft to live. And then a review agent and a testing agent is coming back and then making sure that all of the information is accurate. As a result, it finally gets to a human gate. That human gate is me checking to make sure all the code is running properly. It looks like the thing that I want to build. And then we're deploying it to our deployment pipeline. I've taken every step of the software development lifecycle and tried to map it through our orchestrator. So the orchestrator has different nodes on what to do, where to hit things, on what agents to create. And this orchestrator is actually pushing the information all the way through the software factory. Next, we're going to talk about memory. But before I talk about memory, I'm going to check on some questions. We have one question coming in, which is, I'm noticing it mirrors a lot of established practices. Is there anything that might be missing from this framework? There's 100% probably 1 or 2 things missing from this framework. When we gave this as a case study last week to the Gauntlet Cohort 4, they had so many different ways of building their software factory. The reason I like to call this minimum viable factory is because it's a starting point. It's sort of where we're going to have a foundation or a base layer, and we're going to build on top of that base layer. That base layer is going to get bigger and bigger and bigger, so you can actually optimize this to exactly what you're looking for. If you have a specific deployment pipeline, a specific testing strategy, if you have a specific way you like to write code, you can actually change this factory to match. The next question is, what is the best to use agent as a team and not stepping on each other's toes? So the best way to make sure that the agent is not stepping on each other's toes is coordination. Agent coordination is probably one of the biggest unsolved problems in the market right now, because what tends to happen is if two agents start working on the same file, then they're always going to come together because one is eventually going to compress memory and forget that it was actually even working on this file. So the way I like to do it is if you put a JSON object in the root directory for each agent and what files they're allowed to touch. And if one agent is already currently working on a file, you can actually lock that file. So you lock that file until that agent is complete, so it can come back and then add more to the file later on. As a result, it'll always end up in merge conflicts. If we don't do this, you need some sort of locking strategy, some sort of delineation strategy to say one agent, one file, one at a time. The next follow-up question is, do you update memory as each agent works and send them off with bounded tasks with verifiable exit conditions? 100%. So what we're doing is when we spin up a Docker container and we put a Claude Code instance inside, we decide what memory that agent has. We're saying, hey, this is the memory you're coming in with. This is the task you have. These are the files you're going to work in. And this is exactly what you're supposed to execute. The orchestrator is actually writing the prompt for that agent in the Docker container. So as a result, what we're trying to do is use the orchestrator to figure out what parallel tasks can be done, what tasks cannot be done in parallel, and then deploy those different containers as a result. Question number 4 I'm getting here is, do Gauntlet challengers learn this in the curriculum? The answer is yes. In fact, they presented their software factories to Austin just on Saturday. He hasn't decided a winner, or he hasn't told me who the winner is. But what happens is in Gauntlet, we are presented with a case study. So on Tuesday, they were presented with the software factory case study. They got into groups. They decided on an architecture. They tried to figure out how they would actually build the system. And then they presented that around the entire cohort, and as a result, the entire staff. The goal here is we're trying to think about how to build things from a system design perspective. It's not about the tools. It's not about the code anymore. You can generate really good code really fast. It's about how you design the system. It's about systems thinking. It's about how to make sure that your architecture is scalable, secure, and reliable. And so that is what they were tasked with building just last week. So someone's asking about the credentials layer. So what you're saying with the credentials layer is that we should be able to swap out between major providers with little headache. That is correct. That is the goal. So if you decide to swap out between major providers, all you're doing is you're eliminating an MCP. So the MCP associated with Railway, for example, then you're adding a new MCP, maybe the MCP associated with Supabase, and then you're updating the deploy skill for whatever is required for that deployment pipeline. So there's a 3-step process to changing the credential layer. 1 is updating the MCP connected. 2 is updating the skill connected, so we know exactly what's happening. And then 3 is changing the API key. Domain knowledge would effectively be the limiter regarding the expanding the software factory framework to outside building a web application. So this is an interesting question. So the question inherently is saying, is the only thing stopping this software factory from being applicable across the board domain knowledge? I would argue that currently the software factory that I've built can greenfield web applications pretty well. I think we can make it better, we can optimize it, we can make it cheaper and faster. The next step would be brownfielding, meaning you take a really duct tape, terrible repository, and then we try to make sure that even in a brownfielding task, it's still able to generate really good code. Once we get down there, then what we're really doing is just changing the MCPs for the type of app we're building. So if it's a desktop app, you might need Electron. If it's iOS app, maybe you have a connection out to another UI library for Apple. Long story short is you're just changing the MCPs and skills, And so domain knowledge is definitely one of the things you have to focus on. But I also think that if you're trying to build an application in a different realm, you have to think about the tech stack really well. What are the most common failure modes observed in software factories? And what governance mechanisms have been essential to prevent drift, duplication, or system decay? This is an amazing question. The first thing that you need to have is visibility. Every time somebody makes a software factory or something like it, the thing that's always missing is every single decision that the agent took. Whether it was an agent running in parallel, whether it was an architecture agent, whether it was another agent on top, we need visibility and traces into everything. One of the big reasons I have an orchestrator in LangGraph on top of the entire system is because I want visibility and traces on top of everything. I want to see, why was this agent called? What was this agent doing? What prompt was this agent given? What context was this agent given? And as a result, how did the software factory update that state model from one agent to the next so I can see what's happening? In terms of governance, telemetry is the first step. You need to have all of the traces. You need to make sure that the factory is actually doing the right thing. The second step is evals. So let's say you have visibility into how that factory is functioning. Then what you're going to do is you're going to go into each of the different agents and establish evals. Hey, these are the evals for system design. The system design should always have X, Y, and Z components, and then maybe have LLM as a judge come in and score things, or even have a human come in and score based on the rubric. But the goal would be that if you want to get to proper governance, step one is visibility, step two is evals, and then as a result, those evals can become actual governance checks on top. All right, next question we had is, what are the most common failure modes that have been observed? The most common failure modes are essentially memory decaying, meaning that it's been given a task, but it tends to forget what it's actually trying to do. So it does a random task or it does it incorrectly. The second thing is it's agents not being able to coordinate with each other. This is still an unsolved problem. There's many things out there in the open source space that is trying to solve this, but essentially agents need a way to make sure that they're not stepping on each other's toes. What happens is you'll update a line, then the same line will be updated again, and then you don't know what is actually supposed to happen. So memory decay, agent coordination problems, and then finally evals. As a result, some agents might be getting better prompts, some agents might need more context, so you need to have a nice eval set to make sure you decide what to do when. Okay, next question is, what percentage of the factory output is built from reusable components versus net new code? And what systems enforce reuse before creation? I wish I used reusable components. All of the things being created are net new code. So sometimes it uses a component library, but oftentimes the minimal viable factory right now generates that code on top. Now, you could 100% use reusable components where you had a component library already established, or maybe you had a pattern for your endpoints already established. So as a result, all you would be doing is making sure that it follows those patterns. So the answer to your question for minimal viable factory is very little, probably 10%. Okay, I'm gonna keep going. I'm gonna talk about memory for a little bit. So there are 6 agents involved in the most basic version of minimal viable factory, and none of them remember anything. That is an assumption you have to make. When you're considering deep agents, so deep agents is anything that runs for longer than 10 minutes without human interaction, there are 3 ways to manage context: context compression, context isolation, and context offloading. Context compression is what we see in the chat window all the time. Our chat window starts to get summarized. Our chat window becomes less and less, more and more summaries, loses key information. That's because it's being compressed. The second thing is context isolation. We're going to make a sub-agent, and that sub-agent is going to have very specific context, and that specific context is going to highlight exactly what that sub-agent is doing. And then context offloading is taking all of the information that we have or we're sort of gathering and putting it in a memory graph or a file. Why do I say this? The reason I say this is because when you're building a factory, you have to understand how you can manipulate context, because each agent is going to have a fresh slate. That means every time a Docker container is spun up and every time there's a Claude Code instance inside, there's not enough context there. There's virtually zero context except the memory that you have saved. So what we're doing is we're creating a simple memory system inside of the root directory of our project. That system essentially tells us, hey, this is the linear ticket that's being worked on. These are the updates on it. And then we've even added an audit log. That audit log basically says these are all the actions being done step by step. So this is an example of what that file might look like. You might have LIN23 or linear ticket 23, what you're working on, the actual spec, the architecture, the implementation plan, and that memory is a way for all of the agents to then access that information as necessary. Some people always like to talk about memory graphs in this scenario, meaning like, hey, if you had a memory graph on top of this, you wouldn't need all of these files. I actually think a file system is a better solution to memory than a memory graph, because maintaining that ontology layer on top of a memory graph is very difficult. Making sure that all the connections are correct, that they're not drifting or decaying. As a result, having a really nice skill, and that skill teaches the agent how to go into its memory file system, go into the right files, traverse those files, I think is a really nice solution. And that's the same solution that Anthropic came out with when they launched Skills. Skills is essentially just file system memory that is being progressively disclosed on top of context windows. So what we're trying to do with our memory solution is keep it simple. We're making files for every decision that's being made, tracking all the steps that the agent is taking, and as a result of those steps, moving forward. And then the agents can come back to that memory whenever they need to track any other information. We also have references inside of our memory files. That means if a ticket references another ticket, then the agent knows to traverse to that file to get more information. Okay, there's 3 rules that make our memory model work. You never overwrite. So the big coordination problem between agents is, hey, one agent does this, the other agent does this, and then they update the memory, and then it's completely wrong. In this scenario, if an agent does this, that is now solidified. The agent can come in and then update the previous agent, but they have to make a new log inside of memory. So you have the full history on all of the things that were changed. You want to make sure that you're reading everything per section. So that means if there's a memory or a ticket associated with a certain part of the code base, I am making sure that my agent that's about to work in that part of the code base has read through the memories that is necessary for it to code on top of that. There's also no coordination when it comes to the creation of a memory. You don't want agents going back and forth and deciding what the memory should be. You want one agent to add the memory, that a memory becomes solidified, and then the second agent coming in and adding a memory on top. So this is how it all connects. You have our linear ticket. That linear ticket then is being stored, all the contents of what's happening inside of a memory directory. That memory directory is labeled with a ticket number.md. And what we're doing is we're using that memory to send events to Slack for approval, to Linear for updates as a single source of truth. And each of our agents are just reading and appending, reading and appending, reading and appending. As a result, this file system automatically becomes the memory you need to move forward. Next thing is the orchestrator. The orchestrator is just not a regular a regular script, but rather it has a stop, a start, it has an orchestration, it has everything it needs to actually move all the Dockerized agents as it needs to. The goal here is this orchestrator can actually pause work, meaning if our factory is building 6 apps at once, one of the apps is blocked, well, it can pause work there, and then once we fix that blocker, then it can continue work on the same application. Similarly, if you were to build a factory and you knew that it could only do one thing at a time, if it got blocked and then it was over, you'd have to restart, then it would not be a real factory. The reason we have an orchestrator is because the orchestrator manages the memory, the ticket, the spec, the architecture, and as a result, it even keeps track of the blockers. So when the blocker is resolved, then you can actually just move forward and continue building what you're building. The orchestrator also lets us fan out. That means if we need 18 agents, if we need 3 agents, if we need 2 agents, then we can fan out all the work across each of the containers. Finally, if an agent times out, or if that agent is blocked, or if the agent makes a mistake, or if it loses the work it's doing, the orchestrator still has the information. So it can retry without needing to actually restart the entire cycle. That's why you need an orchestrator, not just a simple script, because it gives you the opportunity to handle all the edge cases. Now, one of the key things when you're building a factory is actually the state. And the state represents what is all of the information that is being tracked in my factory. In my factory right now, I have the repo, the slug, the ticket ID, the branch, the memory path, the subtask, the errors, the state map, all of the different things that are being written down by each of the different agents. I'm actually maintaining this so that my orchestrator knows, hey, this is the agent to call. This agent messed up. I need to retry this agent. Hey, move this down the same deployment pipeline. Each gate is an interrupt, meaning it stops the orchestrator, it sends the message to a human being, where the human being has to do an action to make sure that the factory continues. And what I'm doing is, within that interrupt, I'm saving all my state. And then once I get approval or I need to redo something, I can update state and then I continue down the line. How does it actually restart? The graph is being invoked again with the same state object at the different part of the factory, meaning I can interrupt an entire graph, restart it at a different part, and it shouldn't matter. There's multiple entry points to the same orchestrator. So if I were to show you what the graph looks like from start to decompose, we have the start node, which goes into our PM agent. We have our interrupt, which has the gate. We then resume it based on what I say as the human being should happen next. Then it goes to the architect agent, another gate, and then decompose. The goal here is you're moving from agent to agent with the edges and the nodes and the gates you need to make sure things are going right. This is the same graph running in parallel for all of our dev agents. So once we know exactly what we're building and we've already decided the architecture, we're just fanning out and creating multiple containers, resolving all those containers, and then as a result, checking to see if our review and our test pass. Okay, before I get into integration, I'm going to go back to questions for a second. When looking for an agent, if running a local model, what is a good parameter number to be looking for in a model? This is actually a very good question. Interestingly enough, the parameter number often doesn't directly correlate with how well the model does. So I'm not sure if it's like a specific parameter number, but rather what I would do is if you have like open router, you can try Kimi K2.5, you can try Minimax, you can try Deep Sea Coder. I would rather you try multiple open source models without even considering the parameter. So then for your specific type of code that you're trying to generate, you can actually compare and see which one's working better. How do you make stack decisions for projects or for this project? This is a great question. We have a skill that is making a majority of the decisions on the stack that I've already predefined. But if there's any other libraries, it can add it to the spec. And when I review the spec and the architecture, I can approve those new libraries. So most of the time what I'm doing is I'm taking the tech stack of my company. I'm taking the tech stack of this client. And that tech stack is then being turned into a skill. And then that skill is then being used to decide what to build. But if that tech stack has any changes to it or might need to be changed to optimize something else, then the agent can add that to the spec or the architecture directly. There seems to be heavy reliance on external paid products. Has there really been an examination of the cost running a factory? Historically, we have stayed from hyper-efficient memory usage and performing code as hardware has increased in capacity and performance. Great question. So I ran my factory yesterday to build a Trello and Asana clone. It took about 39 minutes and $21. And then for the Asana clone, it took about the same, which was about 47 minutes and $27. But again, this was low fidelity, right? The UI wasn't like completely there. There was definitely multiple things that we could have done to make the UI better. But in terms of like functionality, things were already working with Supabase and Vercel. Now, the reason why I'm using Claude Max plans inside of Claude Code via the SDK is because it's cheaper and you get way more tokens when you actually stitch those together versus trying to hit the API directly. Now, Langsmith is also showcasing how many tokens we're using on top. And what we've noticed is that even from switching from Opus to Sonnet, there's like an 80% reduction in cost. What we're probably going to add to Minimal Viable Factory next is an adapter for open source models. So you can use Kimi, you can use whatever model you want on top of Open Router, and then maybe the orchestrator decides what model to use when. Now, there's a really nice little framework I like to keep in mind. Have the dumber model generate the code, but have the smarter model review the code. The dumber model will generate the code and generate all of these tokens, and there will 100% be mistakes. But when Opus comes in and reviews the code, it will easily identify those mistakes and you can correct them directly. So those are the two things that we're going to be introducing as a way to fix cost. To do a parallel run, we need shared memory to track, right? That is correct. Great question here. If the runs are happening in parallel, the reason why I have a single issue on linear with sub issues on top is because I need to see all the different things happening. It is also a single MD file that often tracks multiple tickets depending on whatever grouping you want to do. So what you're saying with the credentials there is that we should be able to swap out between major providers with little headache. Okay, little headache is a relative term. So what I'll say is there's probably going to be some headache based on what you're trying to do. Like if you're trying to connect AWS or GCP, it's going to take a second. But if you're doing something simple, a done-for-you deployment service, it should be straightforward. It should just be an API key, an MCP, and a skill. At what point is there regression testing? This is a good question. There is not regression testing yet. There's integration tests and unit tests that are being created by the agent itself. But from a regression testing perspective, there's two thoughts I have. Each agent would need evals, and each of those evals would need tests on top. So we do regression testing on top of that to see if they were performing well. But in this version of the factory, we haven't thought through the actual regression testing strategy, but that could be something we add. Where is the orchestrator hosted and universal? The orchestrator is currently just running locally. Everything is local for my minimal viable factory. The orchestrator is running through a LangGraph instance on my computer. All the dev agents are Docker containers that are being spun up. And on top of that, all the different connections that are happening, I'm using ngrok to get all the webhook events. But as a result of what we've built now, everything is local. Is it possible to do this entire workflow remotely with local open source models? Is there a required amount of compute you need or estimation on how many tokens you say in per week per development? You could 100% do this with open source models. That's actually what we're going to add next. What I would do is take Open Router. I'd create an adapter on top of Open Router, and that adapter could be connected to our minimal viable factory. You can change the models that you're using directly. In terms of token usage and how many per week, you can assume based on the number of apps you're building, you can get upwards of hundreds of thousands of tokens per week. So it's important to understand how much you're going to be giving off to an open source model, how you're going to get the better model to review it, and then how many apps you can try to generate in conjunction. But it is possible. In our setup, when agent A writes to shared memory and agent B reads it, who's responsible for validating that handoff? This is a good question. Agent B is responsible for making sure that it's reading the memory correctly of what's written inside of the file. So agent B has to make sure that it's not editing any file, only reading on top of it. If it decides to append, then it can only append at the bottom. Which I've been considering could be something that we add an outside objective tech check to. But right now, we've just had agent B be the thing that makes sure that the thing is working. Okay, I'm going to finish this up really quickly here. I'm going to talk about the integration layer. I've chosen a tech stack that is familiar to Gauntlet, but again, you can switch this out wherever you'd like. I have a linear MCP, GitHub MCP, Vercel MCP, Supabase MCP, Slack MCP. You can also use CLIs if you don't like MCP. We have 6 skills: spec writing, architecture, coding, test writing, code review, and deploy checklists. Each of these skills are based on how I like to do each of the different aspects of this. If you're working in an engineering organization, you might come together as an organization to decide when and how to deploy each skill and how to create it. The skill is by far one of the most important parts of this, because if you're trying to build this for, let's say, an actual stage, an actual production environment, then the goal should be that it matches what you do normally in your domain. So take some time to actually develop these skills well. I want to talk about observability really quickly. What I've done is I've created a parallel job called pipeline start, which actually maps every single thing that's happening within the pipeline. So I can see using the @traceable on Langsmith what each of the different areas is doing, whether it's a tool call, whether it's an agent, whether it's a Claude query, whatever it is. I want to make sure that I'm seeing it on top of Langsmith. So when you think about observability, I like to think about it this way with all the steps that are being taken. We have the pipeline starting, the pipeline initializing, the agent starting, the gate waiting on me for approval, the subtask being done, an error or a timeout, or my pipeline being done completely. I also have all of the different stages on top of linear. So the agents are actually updating the stages on top of their sub issues. So actually I can see the entire factory running across multiple projects. If I were to go inside of the code, this is the code. I try to keep it as simple as possible. What tends to happen with open source code is there's like hundreds of files, there's random code everywhere. It's really hard to understand. In this case, I tried to make sure that this was really easy to understand. You can actually walk through each of the files and kind of understand what everything's doing. So we have an orchestrator, and it has a config, which is just for our env variables. We have a state.py, which is essentially the state object that we have on top of our orchestrator. We have an audit, which is essentially just logging all the different actions our factory is doing. We have a memory, which is handling the append and the read for each of our agents. We have a linear connection, which is essentially hitting the API, doing all the updates. We have a Slack connection, which is sending me messages for approval. We have our basic agent runner, which establishes the Docker container, adds Claude code via the SDK, and actually imports all the memory and all the information. Then we just have graph.py as my LangGraph orchestrator, and then the pipeline itself. Each of the nodes, each of the memory are just empty directories in the same project. And what I'm trying to do is separate out how each of these things is working so you can actually add more complexity on top later on. So in this scenario, this code is essentially 6 skills, 5 MCPs, and about 7 lines of code, 7 files of code. Now, the awesome part about this is one function runs the entire agent, and then the skills help the agent decide what to do. So there was a big paradigm in the past where we were like, hey, we need to create an agent for all different tasks. Here's our review agent. Here's our writing agent. Here's our proofreading agent. People were creating 18 different agents and then creating teams. The awesome part about what Anthropic built is you have one orchestrator, multiple skills, multiple MCPs, and you can pretty much run anything you would like with the specific context that you need for that task. This is built on that same paradigm. The orchestrator is using the same agent file with different skills and different MCPs to build whatever it needs to. We are also splitting the work, right? I remember when I had one agent just building all the code step by step, it took 63 minutes for it to actually generate even just the front end. The goal here is if you're building a real factory, you need to have multiple assembly lines. Multiple assembly lines means you can run multiple tasks across the board and you can actually walk through each of them. We are at the hour, but I'm going to keep going because I'm in like the groove right now. So we'll definitely answer all your questions as well. So if you want to try this for yourself, there's 4 steps. You're going to clone my repository. That repository is called Minimal Viable Factory. We're going to link it for you here in just a second. And you're going to set up Linear, you're going to set up Slack or whatever tool that you want to use. You're going to have Docker running, the Docker daemon running inside of your computer. You're going to add the keys, the setup, pick your tools, write a ticket, move it into spec, and actually run your factory. What you need is the infrastructure, ngrok, Langsmith, Docker. You need the 6 API keys for whatever you decide to use, and then follow the guide on top of the README. Now, this is my minimum viable factory. This doesn't include everything, all the bells and whistles. It also sometimes clocks out. It has an error here and there. But this is the foundation. We want to work on existing code bases next. We want to have smarter gates, meaning it's not just like a basic gate for spec and architecture. We want to have specialized agents, meaning what if I had an agent that was using a different model, different MCP, different skill, and I could then rotate those agents out as I need. And I want to run on top of my linear instance multiple projects to see where the factory starts to break. So I'm excited for you to take this code yourself. I'm excited for you to take this code and make it your own and actually try to see if you can create your own factories. Now, before I go to Q&A, I want to mention one thing and one thing only, which is this is just a software factory. We could create an SEO factory. We can create a Facebook ads factory. We could create a operations factory. The concept of a factory is really important because in the future, we're going to have AI digital coworkers. These AI digital coworkers are going to be able to take work off our plate. We're going to have different contracts with them, whether that is in marketing, that is in sales, or engineering. This thought process, this experiment, the goal of it was I wanted to open your eyes to the possibility of running all of these functions in parallel. The possibility of being able to actually run all of these tasks and complete something end to end. Because if you could do it for software, you can do it for everything. If we could do it for everything, we're actually moving towards what the future looks like with AI. All right, time for some Q&A. Where's the Git repo? That is the perfect question. So I'm going to share the Git repo really quickly. Good? Try now. All right, sharing. Did you get it? Producer Ariel. Cool. Everybody thank producer Ariel and producer Adam. Okay, this is our Git repository. It's called Minimum Viable Factory. It's on my GitHub account at Tilawat, but we're going to be putting this link to you directly inside of each of the chats. Okay, what heuristics do you use to define thresholds for when an error warrants human review? I've noticed as the context window gets larger, agents tend to go down the rabbit hole and suffer context drift, and in the fix, they apply. This is 100% something that happens over and over and over again. The way I like to do it is, I think that you should structure every coding task into maybe 50 to 100 lines of code. Right? That is a general heuristic to say, this agent should be only doing a task that is maybe medium difficulty. Maybe it's like, if you guys have done story points or something like that before, it's only like a 4, 5, 6, 7, something like that, somewhere in the middle. The thought process there is I want to make sure that the agent is able to complete that task quickly enough that I'm able to port in all the memory and the context, and so that that context does not have to be compressed. The thing that we are fighting is context compression. And because we are fighting context compression, we have to make sure that every task given is medium, it's not too large, it has all the information in one place, and that all of our agents can actually execute on top of it. How does your software factory ensure it produces measurable outcomes rather than high volumes of code, commits, or tools? How do you detect and correct when the factory is busy but not effective? Great question. Langsmith is my primary tool for this. Langsmith actually walks me through everything going wrong. It actually shows me when it's using too many tokens. It actually even shows me all the different prompts that are being inputted. At the same time, if this is at the deployment level, then I have the logs on top of Vercel and Superbase, which I'm porting back to my factory itself. I'm also making sure that on top of linear, I'm making it a point to actually put an update, showcase what's happening so I can go down the linear ticket and see what's going on. Someone is asking, this is great info. Is this going to be a series? 100%. I teach all the time for Gauntlet AI, either way. We have some of our Gauntlet Cohort 4 participants in the audience. So what we're trying to do is make this a series, have a weekly class where people can actually talk about things that are useful, prominent, and at the frontier of AI. What I find is knowledge or topics or content in the AI space is kind of hand wavy. It's kind of random. It kind of doesn't have a way for you to apply things. First and foremost, when we're talking about these different aspects, everybody has their own way of doing things. And the goal should be that we are taking all of these concepts, all of these frameworks, all of these different aspects of what we're doing and trying that out ourselves. So that's why I also wanted to make sure that we had this repository available for you to try out. And if you love what we're doing here, then you can also consider being a participant of Gauntlet Cohort 5. So that's apply.gauntletai.com, where you can go out and go become a Gauntlet Challenger. We have some of the most cracked engineers in the world. We're building together nonstop for 1,000 hours over 10 weeks. And our goal is to be at the frontier of AI and to try new things, to break things, and actually discover different aspects of what's possible when it comes to AI. Okay, next question. How does the orchestrator monitor if an agent critically wanders off task and when to terminate and retry? In this case, it doesn't monitor, but rather just has a simple timeout. So basically says that if it's been more than 10 minutes, go check in on what's happening. If it's not actually updating code in the right area, then terminate that task. So it does not have a specific monitor functionality, rather it just times out directly. For the software factory to be truly self-improving, what telemetry are you capturing from a deployed application to inform the next iteration of the template or blueprint in the factory layer? Great question. In this scenario, we're just porting all the logs from Vercel and Supabase directly. So we haven't captured, let's say, we can have Playwright go onto the actual deployed website and actually run things and click things. We haven't done that yet. In this scenario, what's happening is everything that we're using is just being ported in as logs from the 2 deployment pipelines. Next question is, when does the next cohort of Gauntlet start? That is April 27th. April 27th, right after cohort ends, we're starting the remote section of the next Gauntlet. The amazing part about Gauntlet is the environment. You will never find in your life being the opportunity to be surrounded by 100, 200 cracked engineers all working on AI together. So if you feel like your company's not focusing on AI, you're about to be left behind, or you want to sort of immerse yourselves completely in Gauntlet, then please come join us. Has this design been used since cohort 1? If so, has it evolved to be more efficient? Is your company using this type of model? Great question. In cohort 1, we were mostly using a single Claude code or single cursor. Over time, we've tried using Conductor, different things like BMAD. We've come to this software factory model, especially because of Kelly Claude AI, which if on X you haven't heard, is our OpenClaw instance, also building a software factory. And the thought process here is if you can understand how to build a software factory, if you understand how to architect a software factory, then you're sort of preparing yourself for the next stage of this. Long story short is, has it become more efficient? I think we've become more and more efficient at using a single Claude Code instance or a single Codex instance. I think in terms of the factory, there is a lot to be figured out. The way companies are doing this now is through spec-driven development, meaning you have all the steps of the factory, but everything is sort of human-gated. You create a spec using a product manager, the product manager has to approve. The spec is then brought to the local environment. The spec is then used to create tickets and PRs and so on and so forth. So there is a manual way to do this, which is through spec-driven development, but it has not been completely automated end-to-end. Are you baking policy as code into the generation phase, or is there a separate automated audit factory that validates the output before it hits production? I have a separate agent entirely. That is my testing agent that is auditing everything. It's using the audit log, running test, and integration test on top as a result to actually decide and see if things are working correctly. Now, the thing I need to add is a way to sort of click inside of the browser and actually do things on top. We have not added that yet. But in this scenario, the testing agent is doing it, not a separate layer. All right. What are you going to do next? So we did this class. We talked about a lot of things. I think that each of you should take my minimum viable factory and try to make it your own. Go out, fork it, change the code, map it to exactly where you're using inside of your tech stack, and as a result, try to build your own software factory. This exercise that I'm putting each one of you through is actually going to make your system design, your ability to work with Claude Code, to orchestrate agents on top 10 times better. This is the thing that we need to do. Get our hands on a keyboard, actually try things out, even if they don't work perfectly all the way through, and then see what happens on the other side. Okay, last call for questions. Again, if you're interested in joining Gauntlet Cohort 5, it starts April 27th. It is 3 weeks remote, 7 weeks on site. You're going to be surrounded by some of the most cracked engineers in America, and we're going to be all focused on creating, at the frontier of AI, different applications, different factories, and orchestrating agents at the next level. Apply.gauntletai.com. Apply.gauntletai.com. Any more questions? Are we good? All right. I want to thank everybody for joining me. We'll be back again next week for another edition of Night School. If there's more questions, feel free to add them on top of the GitHub repo. Feel free to do what you would like with the GitHub repo itself. And if you want to access the GitHub repo, it is #Tilawat/minimum viable factory. Thank you again. We'll talk to you soon. See ya.